Okay, so in this lecture, we will discuss about general group theory. Okay, general group theory. Yeah. So first, let us start with an example. Let's say we denote the set of all natural numbers till n as this. Okay, as the block n. Now, what we try to do is that we actually want to consider a set which consists of all bijections of the elements in block n. Okay, so we want to construct a set from block n to block n such that the set sigma is a bijection. Okay, now if I give an example of how sigma works, then notice that so suppose this is sigma, let's say. So suppose we have 1, 2, 3, 4. We consider 4 elements. Okay? And so here also we have 1, 2, 3, 4. So if I try to construct a bijection between them, suppose for example, we construct, suppose we map 1 to 2, we map 2 to 1, we map 3 to 4, and we map 4 to 3 via the bijection sigma. So therefore, sigma of 1 is 2, sigma of 2 is 1, sigma of 3 is 4, and sigma of 4 is 3. Clear? So basically, so we can think of it as, so we are mapping 1 to 2, 2 to 1, 3 to 4, and 4 to 3. Right? Now, obviously, we can view this as rearranging the elements in block 4, right? Or rearranging the elements 1, 2, 3, 4. Okay. And obviously, if we consider all possible bijections from the set 1, 2, 3, 4 to the set 1, 2, 3, 4, then we are, we will be typically getting all possible arrangements of the elements 1, 2, 3, 4, right? And that is indeed what we had studied in the concepts of permutations, right? In the concepts of permutations, right? Got it? So therefore, if I construct a set which consists of all possible bijections from block n to block n, so that set actually consists of all possible permutation of the first n natural numbers, right? And we denote that set as Sn. Okay, so this is often said to be the set of permutations, of the elements 1 to n. Clear? Now, having constructed this set, we observe certain properties in this set. First thing what we do is that we impose a binary operation on this set. And the binary operation is, so since the set consists of functions, so the first binary operation which will obviously come to our mind is the composition, right? Composition of functions. Okay. So consider the set Sn, and with an operation where this is the composition. So this is the composition of functions. So this is the composition of functions. Yeah. Okay. Now notice that if you take two permutations, suppose sigma 1 and sigma 2 from Sn, then sigma 1 composed with sigma 2 is another permutation, right? Is another permutation. Because you know if you consider sigma 1 of sigma 2 of some element I, then this is nothing but sigma 1 of sigma 2 I, right? right? Now if suppose let's say sigma 2 of I, this sends I to some j, then this is indeed sigma 1 of j. And if we know that sigma 1 sends j to some k, so sigma 1 of sigma 2 I, this is nothing but the element k. And obviously sigma 2 and sigma 1 are from Sn, right? So each j and k, they are obviously again elements from block n. So therefore sigma 1 composed with sigma 2 is another permutation. So that means that sigma 1 composed with sigma 2 is again in Sn, right? Now obviously one fact we know about composition of functions, that it's associative in nature, right? That is a typically, uh, a theorem based on simple study of functions. Okay. So we are not gonna dive into that, but we know that associativity holds, right? So let's consider the third observed property. The third observed property is that, let us observe this by an example. So again consider S4. Okay, so it's the set of all bijections from one. So from the set 1 2 3 4 to the set 1 2 3 4. Okay. So suppose I choose an element sigma from S4 such that sigma sends 1 to 2, sigma 2 is sent to 3, sigma 3 is sent to 4, and sigma 4 is sent to 1. Let's say. Now one element is in S4 which actually sends 1 to 1, 2 to 2, 3 to 3, and 4 to 4, right? This is a very evident bijection, and this also is an identity mapping, right? This is an example of an identity map. So we denote this as ID, okay, referring to identity. Now if you compose sigma with identity, what do you get? So whatever number you have here, suppose sigma composed with identity of some element I is obviously, let's say, from 1 to 4 itself. So it's nothing but sigma of I, right? So typically it's sigma itself, right? From the other hand side, if you come down, so if you take identity composed with sigma of I, okay, then this is again sigma of I, right? Because suppose if sigma of I is equals to some number k, then this is identity of k, so that is equals to k itself, and k is sigma of I, right? And this happens for all i's 1 to 4, right? Therefore sigma composed with identity same as identity composed with sigma, which is sigma itself. And see this very description can be inductively extended to any n, right? So therefore there exists an identity transformation or an identity bijection, let's say, in Sn, such that any sigma you take from Sn, sigma composed with identity is same as identity composed with sigma, and it's same as sigma, right? It's same as sigma. The fourth property, notice that. So again, let us choose an example. So suppose we consider, say, two mappings, sigma 1 and sigma 2 from S3, let's say. Okay, so we are considering the permutations on first three elements, first three natural numbers. Okay, now we consider the mappings, let's say, as sigma 1 to be, let's say, it sends 1 to 2, 2 is sent to 3, and 3 is sent back to 1, and sigma 2 is such that 1 is sent to 3, 2 is sent to 1, and 3 is sent to 2. Okay, then what is sigma 1 composed with sigma 2? Okay, so basically notice that, so first we are considering the mappings of sigma 2. Okay, so notice, so this, what does it map? So what is 1 getting mapped to? So sigma 2 sends 1 to 3, right? Right? So sigma 1 composed with sigma 2 of 1 is nothing but sigma 1 of sigma 2 of 1, and 1 is mapped to 3, so this is nothing but sigma 1 of 3, and 3 is mapped back to 1, so this is 1, right? Similarly, so 1 is mapped to 1. If you notice 2 is mapped to, so here 2 is mapped to 1. See, notice here 2 is mapped to 1 and here 1 is mapped back to 2. Therefore 2 is mapped to 2. And here 3 is mapped to 2 and 2 is mapped to 3. Therefore 3 is mapped to 3. Right? Then sigma 1 composed with sigma 2 is nothing but the identity mapping. Because 1 is mapped to 1, 2 is mapped to 2 and 3 is mapped to 3. If you also find out what is sigma 2 composed with sigma 1, then this is again identity. This is again identity. Clear? Now observation is that any sigma you choose from Sn, there always exists, let's say, something called sigma dash in Sn, such that sigma composed with sigma dash is same as sigma dash composed with sigma, and it's equals to identity. Now how can sigma dash be constructed? Just notice this very example. So suppose we are given sigma 1. Okay, suppose we are given sigma 1. So in sigma 1 we are mapping 1 to 2. In sigma 2, in sigma 1 we are mapping 1 to 2, 2 to 3 and 3 to 1. So we construct a mapping sigma 2 such that whatever mappings we have here, we just inverse the image and pre-images. So here, so in sigma 1 we have 3 is mapped to 1. Here we have 1 is mapped to 3. Right? So you can find the correlation between them. Here 2 is mapped to 3. So here we map 3 to 2. And here 2 is mapped to 1. So here we map 1 to 2. Clear? Got it? So the correlation is got. So actually the thing is that whatever mapping we are having in sigma 1, if we just interchange the images and pre-images, then we'll get a new mapping, which is the sigma dash itself. Okay? And when sigma dash is composed with sigma from either side, we get the identity mapping back, which is very evident from the fact how sigma 1 composition sigma 2 works, right? So therefore, the fourth property which we have is that for all sigma in Sn, there exists a unique sigma dash in Sn. Now the uniqueness of sigma dash is also very trivial, right? Because everything depends on what mappings we have in the given sigma, right? Because if 2 is if 2 is mapped to 3 in the given sigma, then in the sigma dash 3 must be mapped to 2. We cannot have any other option here. So sigma 2 must be unique, right? Unique on the basis of sigma, the given permutation. But there exists unique sigma dash in Sn such that sigma composed with sigma dash is same as sigma dash composed with sigma, and is equals to identity. Clear? Got it? So, having these four properties with respect to a certain arbitrary set we have tried to generalize, or rather we have tried to gather out all the possible groups which have similar properties, and that has given rise to the structure we call groups. Okay, let us come to the direct definition of what a group is. One more thing which I missed out here, it's to observe that now when we have studied permutation combination, we know that if we have n elements and we need to permute them, so the number of all possible permutations is nothing but n factorial, and n factorial is itself the cardinality of the set n, because the set Sn is nothing but the set of all possible permutations of n. So that is it. Got it? So now let us come to the concept of a group. Okay, so let me change the style as I'm using. Yeah. Okay. Yeah. Done. Okay. So let G be a non-empty set. Let me write it as a definition. So let G be a non-empty set, and let star be a binary operation. Defined on G. So if you remember what a binary operation is, so it's a, so let me just write it here. So star is the mapping from G cross G to G. Okay. So basically, star being a binary operation actually ensures that the first property which we had considered in Sn, that is, if we take two elements, two arbitrary elements from the set, and we have an operation between them, then the resultant element is also in the set, right? So that is ensured by it being a binary operation, because since this is a binary operation, so any ordered pair of elements A and B you take from G, if you operate them using the star operation, so if you map A star B, so this is obviously mapped to some element, let's say C, but the codomain is G itself, right? So C is in G itself. So that ensures that for all, so this actually ensures that for all AB in G, A star B is in G. So this is analogous to the first property we observed in the case of Sn. And this property is called the closure property. Is the closure property. Clear? So, okay, let this be the first property. The second property says that for all A, B, C in G, A, so this is equal to A star B star C, which is the associative property. This is the associative property. Third property says that for all A in G, there exists some element E in G such that A star E is same as E star A, which is equals to A, and this E is said to be the identity element of G. Clear? And the fourth property is that for all A in G, there exists an element A dash in G such that A with A dash is same as A dash with A, and this is equals to the identity. So A dash is said to be the inverse of A. So if these four properties hold, if the four axioms, I should say, if the four axioms hold, if the axioms hold, then G along with this binary operation star is said to be a group. Is said to be a group. Okay. Now, if in addition there is one more axiom, that is for all, suppose say AB in G, AB is same as BA, then G with respect to the operation star is said to be an abelian group. Is said to be an abelian. Okay. So an obvious example of this is what we just studied. So an obvious example of this is the set Sn along with the composition operation is a group. Is a group. Clear? Number 2, if you consider the set of integers and you consider the usual addition on integers, then that is a group. If you consider the rationals with respect to usual addition, if you consider the reals with respect to their usual addition, in fact the complexes with respect to the usual addition, they all form groups. Next, if you consider the non-zero reals with respect to usual multiplication, non-zero complexes with respect to usual multiplication, they form groups as well. In fact, if you consider Q star as well, non-zero rationals with respect to usual multiplication, this is a group as well. So S star in general means S minus 0. Okay. So whenever I am using the term 0, I should actually refer to what 0 actually arbitrarily means in a group theoretical course. Let us just emphasis on that. So 0 actually indicates to the additive identity of a group. The additive identity of a group. And 1 is actually identified as the multiplicative identity of a group. Multiplicative identity of a group. What do I mean by these statements? Let's say, see, we won't be using the operation star throughout the course, because all the way as we move with the course, the operation is not that specific every time. Okay? The operation is quite arbitrary. It does not need to be specified. And most of our use of these sort of structures primarily lies in using the binary operations of addition and multiplication in some way or the other. Okay. So the basic convention through the course will actually be considering the group G with respect to an addition operation or G with respect to a multiplication operation. Obviously, this addition and multiplication has nothing to do with the usual addition and multiplication which we are pretty much acquainted with while studying integers, reals, and so on and so forth. But they are merely used as symbols basically. Okay. So to denote the binary operation imposed on a set to construct a group, we primarily use the symbols of addition or multiplication. When we use the symbol of addition, then the identity element is denoted as 0. And when we use this multiplication symbol, then the identity element is denoted as 1. If the operation denotation is additive, then the inverse element, which we denote as a dash, that is denoted as minus a, and in case of the multiplication, it is denoted as a inverse. Okay, and all these symbols are kept analogous to our primary denotation of these elements in Z, Q, R, and C. That is our usual number systems. Clear? Got it? So 0 primarily means the additive identity of a group, and 1 primarily means the multiplicative identity of a group. Now, typically speaking, why do we remove the additive identity while constructing multiplicative groups? So that is pretty obvious. If you just correlate with the fact that division by 0 is not possible, so the property is kind of analogous to that. Got it? So the thing is that if you consider 0, so what should be the definition of a multiplicative identity? So it must be that G dot 1 must be equals to 1 dot 0, 1 dot G must be equals to G itself. Right? And with respect to the multiplicative operation, if you construct an inverse element, so what that should be? So G dot G inverse must be equals to G inverse G must be equals to 1. But if G is equal to 0, if G is equals to 0, if G is equal to 0, then 0 becomes 1. But that's kind of a fallacy, right? That is not quite possible. Even symbolically, it's not possible. Clear? Got it? So that's why we remove the concept of additive identity from a group while constructing a multiplicative group. Multiplicative group in the sense that the operation is considered analogous to multiplication. Additive group means the operation is considered analogous to usual addition. Clear? Okay. Yeah. So let us move on with our discussion. Now notice one fact that we know usual addition and usual multiplication, they are commutative in our usual number systems. Right? Therefore, the examples in number 2 and examples in number 3, these are abelian groups. Clear? Example 1 is not an abelian group. You can obviously check it by just simply considering any SN. And considering any sort of permutation from them and check. Okay. That is quite trivial to notice. If you have understood the first set of examples, then that's very trivial to find. For an example, let's consider S3 itself. Let's consider S3. No, yeah, okay. Let's consider S3. Yeah, S3 will do. Let's see. So suppose 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to let's say 1. And on the other hand, let's say there is one more mapping. Let's say we map 1 to 1, 2 is mapped to 3, and 3 is mapped back to 2. Clear? So what is the composition between them? Let's check. So 1 is mapped to 1, and here 1 is mapped to 2. So their composition in yields 1 is mapped to 1, right? So 1 is mapped to 1, and 1 is mapped to 2. 1 is mapped to 1, and here 1 is mapped to 2, right? What is 2 mapped to? So 2 is mapped to 3 here, and 3 is mapped to 1 here. So 2 is mapped back to 1, and here 3 is mapped to 2, and 2 is mapped to 3. So 3 is mapped to itself. Clear? Now suppose I reverse the composition. Okay. So we compose this with this. So what does it yield? So where does 1 go to? Where does 2 goes to? Where does 3 goes to? So 1 goes to 2 here and 2 goes to 3 here, right? 1 goes to 2 here and 2 goes to 1 goes to 2 here and 2 goes to 3 here. So 1 goes to 3 here, right? Here 2 goes to 3 and here 3 goes to 2. So 2 goes to 2 and here 3 goes to 1. Here 1 goes to 1. So 3 goes to 1, right? So notice that these two permutations are not same. Here 1 goes to 2. Here 1 goes to 3. So that is an obvious fact that these two are not same. That means commutativity does not hold actually, right? In an arbitrary essay. Is it clear? Okay. Okay. A few more examples if I talk about, say example number 4, which is actually a non-example, if I should say, that is the integers with respect to multiplication is not a group. Is not a group, and that is quite easy to notice because you have 2 in Z, but 2 inverse is not in Z, right? As 2 inverse is actually 1 by 2 because 1 by 2 multiplied by 2 and 2 multiplied 1 by 2 yields 1, which is the multiplicative identity of Z, but 1 by 2 is not in Z, right? So it's not closed under inverses. That is, the inverse of an element is not in Z. That implies Z is not a group. Clear? So obviously that's it's not mandatory for a set that if it is a group with respect to some operation, it needs to be a group again with respect to some other operation. Okay. Another important example of a group is the group Z mod NZ. We will be having a complete discussion on these type of structures, but if I consider them to be just a set declared now, so it consists of the elements 0 bar, 1 bar, 2 bar, and so on till n bar. So typically speaking, these are the residue classes of it. Or if I speak in a more literal sense, then this is the set of all remainders possible if an arbitrary integer is divided by n. So this is the set of all possible remainders when an integer is divided by n. So this forms a group with respect to addition modulo n. So addition modulo n basically means that, so this is written like this. So this basically means that A plus B, or rather I should say it like this, that A plus modulo n B, if this is equals to R, so that means basically R is the modulo of A plus B with respect to n. Clear? So this forms a, this is very easy to check from here. Clear? Now some important properties of a group structure. Let's check. Property number 1: cancellation laws hold in a group. Cancellation laws hold in a group. Now this is quite trivial to notice because if you have AB is equals to AC, then obviously you can multiply both sides with respect to A inverse, right? So A inverse times AB is equals to A inverse times AC. And then you can apply associativity law. So this is A inverse A times B is equals to A inverse A times C. So this implies, so this is identity element, right? So this is 1 times B is equals to 1 times C. So this means B is equals to C, right? And this happens for all A, B, C in a group G. Obviously, notice that the operation with respect to what G, the group is being considered, that is not something very specific here, right? Something very important here. So we are simply using the multiplicative notation. Okay, that is what we are actually be doing throughout the in any possible lecture I will be bringing out a group theory. Clear? Okay. So this is typically called the left cancellation. Okay, this is typically called the left cancellation. Now on an analogous set of steps, we can also form what we call the right cancellation. Suppose we have BA equal to CA, then that would imply BA times A inverse is same as CA times A inverse. That would mean B times AA inverse is equals to C times AA inverse, and that would mean B equal to C because AA inverse is identity. Clear? Let us take the next property. Next property is also very simple. That is the identity element of a group. The identity element of a group is unique. So we can prove it like, let's say, let's do this color. No, suppose E and E dash are two identities of G. Okay, E not equal to E dash are two identities of G. Then E composed with E dash, sorry, I mean E times E dash is E, as E dash is an identity element. Again, E dash is E dash itself, as E is an identity element. So from these two statements, it's clear that E must be equals to E dash. Okay, so that's kind of, you might say that so these are contradiction, hence they must be same like that or sort. Yeah. The third property says that for all elements G1, G2 in a G, where G is a group, so G1, G2 whole inverse is equals to G2 inverse, G1 inverse. Now how can we prove this? So see, G1, G2 whole inverse multiplied with G1, G2. So this must yield identity, right? But you can multiply with G1 inverse from the left. Notice one thing here, since we are not sure whether the elements in a group commute or not, multiplication from the left and multiplication from the right are not same, right? Because that would mean that we are, being sure about commutativity, but that is not the fact here. So we are multiplicating with G1 inverse from the left. So then G1 will obviously vanish by associativity. So we are not writing that. So that means G2 times G1 G2 inverse is equals to G1 inverse. Then again, if you multiply with G2 inverse from the left, then this G2 will vanish by associativity. So this gives us G1 G2 inverse is equals to, since we are multiplying by G2 inverse from the left, so this is equals to G2 inverse, G1 inverse. Clear? Okay, that is what we intended to prove. The next important aspect of a group is the formation of a Cayley table. So Cayley table is typically a table which consists of all possible combinations of the elements inside the group with respect to the binary operation defined on it. So let us simply explain this with the help of an example. Consider the element Z4. So, or rather I should say, consider the element Z upon 4Z. So this consists of the element 0 bar, 1 bar, 2 bar, 3 bar, and technically speaking, we can consider them to be the integers 0, 1, 2, 3 as well, because they simply behave like that only. And we know that it forms a group with respect to the addition modulo 4. So that's from the Cayley table. So Cayley table is simply basically a set of rows and columns. So we have one row here, we have another column here, one column here, one column here, right? So each column consists of the elements. So they represent the element basically. So this is 0 bar, 1 bar, 2 bar, and 3 bar. And here also you have the things. So this is 0 bar, 1 bar, 2 bar, and 3 bar. And here you indicate what the operation you are using. So simply we, as we move along a row, we fix the element which the row represents, and we keep on, operating that element with the elements corresponding to each column. Okay. So 0 bar with 0 bar is 0 bar. Okay. 0 bar with 1 bar is 1 bar. 0 bar with 2 bar is 2 bar, and 0 bar with 3 bar is 3 bar. Then 1 bar with 0 bar is 1 bar. 1 bar with 1 bar is 2 bar. 1 bar with 2 bar is 3 bar. And 1 bar with 3 bar is 4 bar. But 4 bar modulo 4 is 0 bar. So this is 0 bar. Similarly, this is 2 bar, 3 bar, 0 bar, 1 bar. And this is 3 bar, 0 bar, 1 bar, and 2 bar. Is it okay? Clear? Now, what is the need of a Cayley table? So basically the Cayley table actually it brings out the inner structure of a group, right? Because you have a visualization of all the elements present inside the group and how they behave with the other elements, right? The Cayley table actually exposes the structure of the group, right? It actually exposes the structure of the group, the structure of the group. We have a term related to two specific groups in hand, which we call an isomorphism. So we will be having a detailed discussion on isomorphism in some later topic related to groups. But if I give a brief, just an overview of what it is. So two groups, if they have the same group structure, are called isomorphic groups in very typical sense. For example, suppose consider the group Z by 2Z. So this consists of the element 0 bar and 1 bar, and okay, let me just review this with respect to this element only. Okay, let's do one thing. We don't need a new example. We just have an example of this only. Suppose we consider an element G, which consists of the elements identity. So this is an arbitrary group. So it's the identity, an element A and element B. And since we know that the composition of two elements must also be a composition of two elements in the sense the operation behaving on two elements. So operation behaving on two elements must also be in G. So we consider the element AB. Clear? Now we define the mapping on AB like. So obviously, suppose we consider the mapping to be the multiplicative mapping only. The symbol we use is multiplication only. And okay, since we have already used, okay, let the identity be 1 only. We symbolize just 1 only. Okay, so how do we define the operation? So suppose we define the operation as, so 1 times 1 is 1, 1 times A is equals to A times 1 is equals to A, 1 times B is equals to B times 1 is equals to B. So this is typical. Right? We define, let's say, A times B to be equal to B times A. Clear? This will indeed happen in a 4 group. This will actually happen. The reason being, let me just explore this first. See, in this group, so what I claim is that this group is abelian. I claim this group is abelian. So in other words, any arbitrary group with respect to, which has 4 elements is abelian. Or there is a very important theorem, which we will not be having time to prove this theorem in this very lecture, but we will always try to do this in some other lecture. That is, if G is a group with elements less than equal to 5, then G is abelian. So any group with less than equal to 5 number of elements is always abelian. Now, why is this abelian? See, if you consider the element BA, then BA must be in G by the closure property. So that implies either BA must be equal to 1, right? BA must be equal to A, or BA must be equal to B, or BA must be equal to AB. And if this happens, then it's necessarily abelian, right? So now the thing is that, will these things happen? See, if BA is equals to 1, then that would imply A is equals to B inverse. But that would imply AB is equals to 1. But the way the group is structurized, it is obvious that AB is not equal to 1. AB is a non-identity element, right? Because AB is defined to be a distinct element inside the group G. And after all, G is a set, so repetition is not allowed, obviously, right? So this is the contradiction. This can't happen. If this happens, then that would immediately imply that B is identity, but that is also not happen. That can also not happen, right? Because B is also structurized as a non-identity element in G. Similar case here, this would imply A is equals to 1, which is also not possible to happen inside G. So the only possibility left is BA is equals to AB, and that would imply that G is abelian. Okay, G is abelian. So if G is abelian, then this is obvious that all elements AB must be equal to BA. Yeah. Now, so what we do is that, So what is A dot AB? So A dot AB we define to be as, let's say the identity one. Okay. BAB is mapped to be A. Clear? Got it? So AAB is mapped to be 1 and BAB is mapped to be A. Clear? Is there any other operation which we need to define? I guess not, right? Okay. Let us find find the KLU table. Let us do it here only. So 1A B AB. Here we have 1A B AB. So 1 times 1 is 1. So 1 times A is A, 1 times B is B, and 1 times AB is AB. A times 1 is 1. Okay, we need to define what is A squared or what is AA, right? So we define AA to be B. Okay. So AA is B. We have AB here. So that is typically AB itself. And AAB we define to be 1. This is 1. Clear? Next we have B. We have BA. And we know that this is commutative, right? So BA is nothing but AB. And we have B squared. So we define B squared to be A. B squared means B times B. So B times B to be A. Okay. Am I doing it right? No, I have defined BAB to be A, right? So B squared B1. So B square B1. Okay, let me just erase this part. Yeah. Okay. So let me just define B square to be 1 and B times AB to be A. Okay. Then here you have AB. AB correct. Then ABA is nothing but AAB, so this is 1. ABB is A and ABAB. So ABAB. Let us define this to be B. So let us define this to be B. Clear? So this is the way we have defined the operation. Now with respect to this operation, you can obviously notice that this forms a group. G forms a group. Clear? Moreover, notice that you can relate this Cayley table with this Cayley table by simply considering 1 behaving as the 0 element, clear? A behaving as the 1 element in Z mod 4Z. B behaving as the 2 element and AB behaving as the 3 element. Okay. So typically speaking, that these two groups are having the same structure, same group structure. So they must be isomorphic to each other. Clear? They must be isomorphic to each other. Got it? So we can typically say that Z mod 4Z is isomorphic to a group G with elements 1, A, B, and AB, which are isomorphic to this. Clear? Okay. So yeah, that's a good construction. That's a very good definition of it. We will have a much more mathematically concrete definition of isomorphism later. Okay. Similarly, if you consider a group 0 or if you consider a group 1 A B with 3 elements, then you can relate this group structure to Z mod 3Z by the way I related this. So this again forms an isomorphism. Similarly, if you consider the group G is equals to 1A, you can further relate this to this. That will again give you a an isomorphism, things of that sort. Yeah. Okay. Yeah, okay. So having defined this, let us, should we discuss something more, or it's already a 45-minute lecture. Let us give a few definitions. Definition one. So a non-empty subset of a group G, where G is a group, is said to be a subgroup. Is said to be a subgroup of G if, as you can say, if and only if H is a group with respect to the same binary operation defined on G. So basically, a non-empty subset of G is a subgroup if G is a group in its own right. That is, G is a group itself, and the operation is the same one which is getting operated on G. Obviously, the binary operation is restricted to the domain H, but that's the thing. The operation is the same. Clear? For example, if you consider the group Q with respect to addition, then Z with respect to addition forms a subgroup of it, right? We define, so this is the notation used for subgroups. Rather, we will be using for subgroups. So Z with respect to addition is a subgroup of Q plus, right? Yeah, okay. And notice that, no, H is a subgroup of G. Let me denote this as an observation, let's say, observation. H is a subgroup of G if and only if for all A, B in G, for all AB in H, AB belongs to H and B inverse is in H. That is, H is closed under, the binary operation and its inverse. Okay. So the other properties are actually, they are automatically brought down to H from G, nothing else. So the associativity is there because H is subset of G itself. Now, if we can actually prove this in very simple terms, because see, if H is a subgroup, then these two will hold automatically by the definition of a group. Now, if these two hold, suppose for all A, B in H, A, B belong to H and B inverse belong to H, then we can say that A inverse belong to H as well, because A is an element of H. So if A is an element of H, A inverse is an element of H. So A with A inverse, A multiplied to A inverse, let's say, will also be an element of H. That would be one is an element of H. So inverse is there, identity is there, associativity is already from G. Closure property also holds. That means H is a group, right? Moreover, if G is abelian, then H is also abelian because H is a subset of G itself. So this is the criteria you already need to check whether to just find whether H is a subgroup of G or not. Clear? Clear. For example, the one example we just gave here. Another concrete example is, let us consider the group S3. Let small s belong to S3 such that small s is the permutation. So 1, 2, 3. This is the usual notation used to describe permutation. So on the so we form a matrix kind of a structure. The first row contains the element which we are permuting, and corresponding to each element, the bottom column contains the image of that element. So let's say 1 is being sent to 2, 2 is being sent to 1, and 3 is sent to itself. Okay. So basically, A, B, or as I say, A1, A2 till say AN. So here we write B1, B2 till Bn. So this typically means AI is sent to Bi for all I is equals to 1. This is the notation used. One more notation we have, which is called the cycle notation. That is also very easy to notice. A cycle notation. a cycle notation. So if we write something of this form, so let's say I1, I2 till IN, this notation inside a permutation group. So this implies that very permutation which sends I1 to I2, I2 to I3, so on till IN minus 1 to IN and IN back to I1. Clear? So this gives the cycle notation. So if you impose this cycle notation here, then you can notice that 1 is sent to 2 and 2 is sent to 1. So 1, 2 forms a cycle. And this can easily be composed with the singleton cycle 3 because 3 is sent to itself. So actually we don't need to write that again because that acts as an identity operation which fixes 3, or rather I should say a permutation which fixes 3. So something which fixes 3 need not be included in the cycle operation. So something which fixes some element that need not be included in a cyclic operation, cycle notation when we are deriving a cycle notation from a given permutation. Details will be covered in some dedicated lecture to the permutation group, but here we are just considering them as example. So if you consider S to be the cycle, then the set 1S, where 1 obviously represents the identity permutation. So this is a subgroup of S3. Clear? So S inverse is basically the permutation 2, 1. Identity is 1. Got it? Clear? Some other important definitions, let's say, suppose we have, let G be a group, let G be a group, let a small g belong to capital G. We define the order of G denoted as O of G as the least positive integer D such that G to the power D is equals to the identity. Or if I consider G in additive notation, then this is analogous to writing D times G is equals to 0. So G times D, what does G times D actually mean? So let me just write it in a rough here. So G times D actually means G with G and so on, D times, right? So if it is an additive notation, so this is analogous to writing G plus G plus G D times. So that is nothing but D times G, right? So that is it. Clear? So this is the order of an element in a group. Okay, I'm coming 1 second. Yeah, okay. So this is the order of an element in a group. Clear? Now there are very important properties of the order of an element in a group. Let us just explore a few of them. So number 1, if, rather I should say like this, that consider a finite group, let's say. Okay. Or let us not mention the group itself. Okay. Suppose let order of an element G be D. Then G to the power n is equals to 1 if and only if D divides n. Okay. That is, if you have a positive, or rather I should, one more thing I should add here. If there does not exist some D greater than 0 in n obviously, such that G to the power n is equals to 1, then we say that the order of the group is infinite. Okay. Or we often say the order of the group is 0. Sorry, order of the element is 0. Or order of the element is identity. There are multiple terms used. Okay. If we require such a case, we'll try to use the term the order of the element is infinite, let's say. Okay. So If the order of G is some T, then G to the power N equals to 1. This is possible if and only if D divides N. Okay, so let us try to prove this. Now notice that if D divides N, then there exists some positive integer K such that N is equals to dk. Therefore, G to the power N is nothing but G to the power dk, which is nothing but G to the power D whole to the power K, and G to the power D is 1 because order of G is D. So this is equals to 1, right? Conversely, by Euclidean division lemma, we can say that there exists positive integers Q and R such that N can be represented as D, Q plus R. That is, we are simply dividing N by D. Q is the quotient of the division and R is the remainder of the division. Okay, where R is 0 or R is less than D. So we can write it as, say, 0 less than equals to R less than D. Clear? No, so suppose this happens, then that implies N minus dq equals to R. But that implies that a to the power N minus dq is equals to a to the power R. But now we know that a to the power N is 1. I was using the element G, right? So G to the power N is 1 because we have assumed that. And the order of the element G is D. So G to the power D is also 1. If I write the left hand side as G to the power N times G to the power D whole to the power minus Q is equals to G to the power R. So that would imply 1 is equals to G to the power R. Now if R is less than D, then it's a contradiction. Because D was defined to be the least positive integer such that G to the power D is equals to 1. And if R is less than D and it is greater than 0, then that's not possible because R becomes the least element now. But D must be the least element, right? So that's a contradiction. Therefore, the only possibility is that R must be equal to 0. And if R is equals to 0, then that is the other way of speaking that D divides N. So this implies D divides N. Clear? Now there are multiple properties related to the orders. We will discuss that in some other lecture. One more important definition related to elements in a group is the definition of conjugates. Okay, so if I consider two elements from a group G. Okay, if I consider two elements from a group G, let G and G dash belong to a group G. G is a group. Then G and G dash are said to be conjugates. If there exists some element U in G such that G can be written as U, G dash, U inverse. Okay. Having defined this, there is one more way of approaching the definition of an conjugate. Let us just come to that. What we do is that let G be a group. Define a relation on G such that, so an element small g is related to G dash if and only if there exists some element U in G such that G can be written as U, G, G dash, U inverse. Okay. Notice that this is an equivalence relation because number one, so G is related to itself as G can be written as 1, G, 1 inverse. And 1 inverse is 1 itself and 1 is an element of G. Right. Number two, so if G is related to G dash, then that would imply there exists some U in G such that G can be written as U, G, U inverse, U, G dash, U inverse. But that would mean that G dash can be written as U inverse G U, and this is same as writing as U inverse G U inverse whole inverse. because you can obviously prove this, that U inverse whole inverse is nothing but U. Clear? Because see, U inverse whole inverse by definition times U inverse, this must be equals to 1. So that would imply U inverse whole inverse. If you write multiply with, you know, with this, this will give you inverse whole inverse is equals to U. Okay. Okay. That is, if you write multiply with U itself, it will do. Right? Okay. So yeah, and the third property is somewhat similar to this, which is, so if G is related to G dash, then that implies there exists some U in G, such that G can be written as U G dash U inverse. If G dash is related to some H in G, so that would imply there exists some element, say U dash, or rather use the element Q in G, such that G dash can be written as Q H Q inverse. So if you put this representation here, then you get G to be the element U Q H Q inverse U inverse, right? So this is by associativity, this is U Q H Q inverse U inverse, and Q inverse U inverse, this by definition is nothing but UQ whole inverse, right? So this is UQ whole inverse. By closure, obviously UQ is inside G, so that means G is related to H. Therefore, this relation is a equivalence relation. So therefore, this is an equivalence relation. So obviously, if we have an equivalence relation, then we obviously have equivalent classes. Right? So define the equivalence class of G to be the set of all those elements G dash in G, such that G dash is related to G. These classes are called the conjugacy classes. Called the conjugacy classes of G. And obviously, since this is an equivalence relation, we know equivalence classes partitions the group G. So G can be thought of as the, you know, as the union, as the disjoint union of the conjugacy classes of each G. Clear? Got it? Okay. One more very important property of conjugates is that, so, you know, if G and G dash are conjugates, so we use this notation only. If G and G dash are conjugates, then order of G is same as order of G dash. So how do we try to prove this? See, one thing you can prove, see, notice that if G is equals to U G dash U inverse for some U in G, then what is G squared? So this is U G dash U inverse times U G dash U inverse. So this is basically U, so by associativity, this is U G dash. So if you associate U inverse and U here, that gives you identity. So it is U G dash squared U inverse. So you can obviously extend this using induction to show that G to the power n is equals to U G dash to the power n. You can show that G to the power n is equals to U G dash to the power n U inverse for all n in n. Clear? Now we will use this fact only. Now suppose order of G is D, then G to the power D is equals to 1, but G to the power D is nothing but U G dash U inverse whole to the power D equals to 1, and we have just proved that this is nothing but U G dash D U inverse equals to 1. Now if you right multiply by U and left multiply by U inverse, so you get G dash D to be 1. Now actually we have not declared what the order of G dash is basically. So we cannot say that the order of G dash is D directly. But one thing we can say that this implies that order of G dash divides D, right? Because we know that if an element to the power n is 1, then the order of the element must divide that exponent, right? So this is say 1. But notice now that if G is conjugate of G dash, then that is the other way of saying G dash is a conjugate of G again, right? G dash is again a conjugate of G. But that would mean that G dash can be written as U. So if we consider some other value, so let's say it is R G R inverse. So that would mean that G dash to the power the order of G dash, let's say, which is equals to R G to the power order of G dash times R inverse, and we know this must be equal to 1. So again, if we right multiply by R and left multiply by R inverse, we will get G to the power order of G dash to be 1. But we know the order of G is D. So again we use that same theorem we had, that if G to the power n is equals to 1, then order of G must divide n. So this implies D must divide order of G dash. This is 2. So 1 and 2 immediately imply that D must be equal to order of G dash. Because we have this case, right, that n divides m and m divides n. So this ordinarily implies m must be equal to. Right? Clear? Okay. Now, if I consider, okay, let us consider one more important topic in groups, general group theory, which is let G be a group and let H be a subgroup of G. Let H be a subgroup of G. Okay. Define an equivalence relation, or rather define a relation. We use the same symbol such that, so we say A is related to B if and only if AB inverse is in H. So we define this relation on G such that two elements in G are related to each other if and only if AB inverse is in H. Okay. You can again notice that this relation is an equivalence relation because number one, A is obviously related to itself, as A inverse is the identity, which is obviously in H since H is a group, right? Number two, if A is related to B, then that would imply that AB inverse is in H, but that would imply the inverse of AB inverse is also in H, because right, because H is a group. So that means AB inverse whole inverse is in H, and that implies BA inverse is in H, and that implies that B is related to it. Similarly, if you have A is related to B, then that implies AB inverse is in H. If you have B related to C, then that implies BC inverse is in H, and that would imply AB inverse times BC inverse by closure is in H, and that implies, so if you associate B inverse and B, then that gives the identity, so that implies AC inverse is in H, and that implies A is related to C. Therefore this is an equivalence relation, right? This is an equivalence relation. Okay. Then as we know that this is the reflexive property, right? This is the reflexive property, this is the symmetric property, and this is the transitive property. Clear? Now, so again, if we have an equivalence relation, then we obviously have an equivalence class, right? So what is the equivalence class of A? So this is the set of all the elements X in G such that X is related to A. So this is set of all the elements X in G such that XA inverse is in H. So this is all the elements X in G such that, so if it is an H, we can consider XA inverse to be equal to some H, right? What I mean to say that if this is an H, then we can consider this to be some element small h in capital H. That means that X is of the form HA, right? This is of the form XA, where H is in capital H. H is in capital H. So this is the set of all the elements HA such that H is in capital H, and this we define as the set capital HA, and this is said to be the right coset of H in G, as A varies over the elements in G. Clear? Got it? Okay. A similar definition we can also use as, let's say A is so A is related to B if and only if A inverse B is in H. Okay. Then it is obviously reflexive. If A inverse B is in H, then the whole inverse is also in H. Then B inverse A is in H, so that means it's symmetric. If A, what is A inverse B composed with? No, it won't be transitive, right? It won't be transitive. Yeah. No, we cannot define this in this manner. We cannot define this in this manner though. A inverse B won't help you. Yeah, but yeah, we will define. The thing I want is we will discuss it later. So this is basically called the right coset of H. Whatever. Okay. So it's called the right coset of H, and so since this is the equivalence class, so it obviously partitions G, right? So G can be written as the disjoint union over the elements A in G with H. So this necessarily also means that the order of G is the summation over A in G, and order of each HA. Order of G, basically, let me just define it. If G is a finite group, we define the order of a group with respect to whenever it's finite only. If G is a finite group, then the order of G is the cardinality of G. Okay. No, we know that if G is a finite group, then the cardinality of the group actually makes some sense, right? In case of infinite sets, the cardinality doesn't make that much sense, but in order to make some sense out of them, we just restrict to the fact that they are infinite. But to be very strictly mathematical, a finite group has the sense of having some cardinality. Whatever bit. Okay, so this is the thing. Clear? Now, suppose I have a function phi from H to HA such that every element small h is mapped to small h A. Then this is obviously A is fixed for some fixed A. Fixed A in G, we define this mapping. Then obviously this is a bijection, right? This is typically a bijection because onto is very trivial to notice. Right, onto is very trivial to notice. Furthermore, if you have say H1A equal to H2A, then you can just right multiply by A, right? You will get H1 equal to H2. Yeah. So this is a 1-1 as well. So this is an evidently a bijection. So if this is a bijection, then that would mean that the cardinality of H is equals to cardinality of HA, right? Now obviously cardinality makes sense here as well because G is a finite group and it is a subgroup of G. Obviously HA is a subset of G as well, which is very trivial to notice from the definition of HA. Now Um, so if I apply this to this statement here, then I would get that the order of G is the summation over A in G of the order of H. But if you repeatedly order, this is the formation like order of H plus order of H plus order of H and so on. Now, moreover, notice that this very statement actually gives that this summation actually gives you the number of right cosets G has, right? Because this summation varies till the number of over the number of right cosets G has. So if I write this as some k times order of G, then obviously k represents the number of distinct right cosets G has, and we denote it for the moment as, let's say, G colon H subscript R. Okay, so this is written as G colon H subscript R. So now this is obviously it measures the number of something existing. That's obviously a positive integer, and if this is a positive integer, so that typically means that the order of H divides the order of G, and this is the famous Lagrange's theorem. Lagrange's theorem of groups. That is, the Lagrange's theorem of groups says that. So what does this basically speak? So if G is a finite group, and H is a subgroup of G, then the order of H divides the order of G. This is the Lagrange's theorem of groups. Okay, and the quotient of this division is evidently the number of distinct right cosets it has. Clear? Okay. So by the way, HA is defined. So HA is typically defined as the elements of the form HA, such that A is in G. Right? Analogous to this, we can also define AH to be the elements of the form AH such that A belongs to, sorry. So this is AH is defined as, because when we are defining this, A is fixed, right? So this is H belongs to capital H. Yeah. So this is H belongs to capital H. So these sets are called the left cosets. Okay. A very so on the overview, the every left cosets are right cosets are two distinct group structures. Okay, left and right cosets are two distinct group structures. We have plenty of examples though. I don't think we have much time left to have a discussion on such examples. So I just want to give an overview of what I'm trying to speak. But if H is a subgroup of G such that GH is equals to HG for all G in G. That is, every left coset of H in G is a right coset of H in G as well. Then, or the other way of saying this as GH G inverse is equals to H for all G in G. Then H is said to be a normal subgroup of G and denoted as H normal G. Okay. If H is a normal subgroup of G, then define, because if H is normal in G, then we can ultimately use the term cosets of H in G, because there is nothing distinct in speaking of the left and right cosets, because they are identical by the definition of H being normal in G, right? Then define the set G mod H as the set of all left cosets, such that G is in capital G. Clear? Now this is same as the defining it to be the set of all right, because they are now the same. Okay. Then G mod H forms a group again, is a group where two elements, let's say GH, or say let G1H, G2H, and multiplied with this operation is nothing but G1, G2H. Okay. So if I consider this to be 1, associativity holds trivially with this operation, because G1, G2, and if you have one more element G3, so these are the elements from the group G, and group G associates these elements. So that's quite trivial. The identity element of G mod H is H itself. Okay, because if you say G1H times some EH, or let's say G1H some G2H is equals to G1H, then what happens? So that means G1 G2H is equals to G1H, right? Right? So is equals to G1H. So that means, so what does that typically mean? So that typically means that, you know, G1 G2 some H1 is equals to G1 H2, but H1 and H2 are elements from capital H. We can cancel G1 from both the sides, so we get G2 H1 is equals to H2, which means G2 is equals to H2 H1 inverse by right multiplication with H1 inverse, right? But that means that G2 is in H. That typically means that G2 is in H. So if G2 is in H, then it is obvious, right, that G2 is in H means G2 times H is H. Because if G2 is in H, so every element you take and you compose that with an element of H, you get every element of H itself. This is very trivial. So what does this mean? So this means from here that G1H is equals to H. So G1H times H is equals to H. So sorry, G1H composed with H is equals to G1H. And the other way around is also trivial. So H is the identity element, and the inverse element is G1H whole inverse is nothing but G1 inverse H. Clear? Clear? One thing you can obviously notice over this group is basically called the quotient group. This group is called the quotient group of H over G. Notice that if G1H equals G2H, where G1 and G2 are from elements from G, then this implies G1, G2 inverse are in G. And why is this true? So this is true basically because from the fact directly relating to the way the cosets are actually constructed. If I consider the example, let us consider this example using right cosets. That will be easier. So if I consider this, say HG1 is equals to HG2, then I mean to say that then G1 G2 inverse is in H. Why is it so? Because if HG1 is equals to HG2, then that would so they are basically equivalent classes, right? The way the right cosets were constructed. So that means the equivalence class of G1 is equal to the equivalence class of G2. But that means G1 is related to G2 by the definition of equivalence classes. And if G1 is related to G2, what does that mean? So this means G1 G2 inverse is in H. Right? I think this was the definition only, or it was G2 G1 inverse. I don't exactly remember. Let's just check. Let's just check. Yeah, so A is related to B if and only if AB inverse. Yeah, correct. Right? Got it? This is a very important. So I don't think I should discuss anything more at this moment. Yeah, so let this lecture be up till this much. In the next lecture, we will be speaking about functions related to group structures. Okay. So meet you guys in the next lecture.